Now let us run another application about the central limit theorem. This time we are going to apply the central limit theorem to the Poisson random variable. Now the question here says that the number of students who enroll in a course is a Poisson random variable with mean 100. Bir derse kayıt yaptıran öğrenci sayısı ortalaması 100 olan bir Poisson rastsal değişkeniymiş arkadaşlar. If 110 or more students enroll, the lecturer will teach the course in two separate sections. Eğer 110 ya da daha fazla öğrenci kayıt olursa dersin hocası bu dersi iki ayrı section'da verecekmiş. Whereas if fewer than 110 students enroll, the lecturer will offer a single section. Eğer 110 öğrenciden daha az kayıt olursa da o zaman tek section halinde verecekmiş. What is the probability that the lecturer will offer two sections? İki section açılma olasılığı nedir diye soruyor. So we say that X denotes the number of students who will enroll to the course. Therefore, X is a Poisson random variable with rate parameter equal to 100. So this is the random variable that is in our interest. And the desired probability is what? For the lecturer to offer two sections, the number of registrations, the number of enrollments to the course should be at least 110. And what is the probability of X being greater than or equal to 110? We need to run a summation of the probability mass function of the Poisson random variable here from 110 to infinity. And that probability mass function is e to the power minus lambda 100 minus lambda. Lambda is 100 here. Times lambda to the power I over I factorial. Now, imagine you are calculating that value just for 110. So let's do that. Again, let me show you that practice. So e to the power minus 100 times 100 to the power 110. Now, the final thing that I'm going to do is going to be too complicated. Okay, factorial 110. Now you see it has calculated that probability. But if you intend to do it by yourself, for example, if you intend to calculate just 100 to the power 110, you will get something like this. And when you intend to calculate the factorial of 110, you would get something like this. Now your calculator, your humble calculator during an exam cannot do that, okay? I mean, the computer here can do that, but your humble calculator cannot do that. Now, I am not just going to do that for 110. I am going to do the same thing from all possible values from 110 to infinity, or you can do the other way. I can calculate the probability mass values from 0 to 109 and subtract the sum of these probability mass values from 1 to end up with my desired probability. Now, I mean, this calculator, this program here can help me to calculate that probability. This comment, and that probability is approximately 0.1705 or 0.1706, let's just say. And as you can see, that probability is computed already by a computer. However, I mean, if you intend to do this operation manually, it would be impossible. But what you know about the Poisson random variables? A Poisson random variable has a large rate parameter here. So the rate parameter lambda is very large enough. According to the central limit theorem, if the rate parameter lambda is large for a Poisson random variable, it can be approximated with a normal random variable with the same expected value and variance. So why can we do that? Because if you remember from yesterday's lecture, a Poisson random variable is or can be represented as the sum of independent Poisson random variables. Okay? So remember, the sum of two Poisson random variables, if they are independent, is a Poisson random variable. So imagine now, instead of having a single Poisson random variable with rate parameter lambda being equal to 100, imagine you have 100 Poisson random variables, all of which has the rate parameter equal to 1. And their summation is going to be another Poisson random variable with this rate parameter. So this Poisson random variable can be expressed as the sum of independent and identically distributed Poisson random variables with rate parameter 1. Therefore, since the rate parameter here is large enough, we say that the random variable x here is a Poisson random variable with rate parameter 100, and its expected value and variance is equal to 100 as well. If you remember, the rate parameter in the Poisson random variable equals to the expected value and the variance. Now we can approximate that Poisson random variable with a normal random variable, which is continuous, with location parameter 100, which is exactly equal to the expected value, and the scale parameter, which is the standard deviation, or in other words, the square root of the variance, which is going to be equal to the square root of 100, that is 10. And then we know that the probability of opening 2 sections, or the probability of the number of enrollments to the course to be greater than or equal to 110 is going to be approximated by the normal probability of x prime, which is the approximate normal random variable, to be greater than 109.5. Why so? Because I am including 110 here this time. 110 is included. So since this is included, for that integer, I am going to take an interval for the continuous random variable, which is minus plus 0.5 away from that integer. So I need to calculate that greater than or equal to probability with a continuous approximation of x prime to be greater than 109.5. And the rest is easy. I will simply standardize that normal probability. So I know the location parameter is 100 and the scale parameter is 10. I apply the standardization to the both sides, and that becomes the probability of z being greater than 0.95. And that tail probability for a standard normal random variable can be computed by 1 minus the cumulative distribution function at 0.95. And that cumulative probability is 0.8289. Subtracted from 1, you get 0.1711. And with that probability, with 17% probability approximately, the lecturer offers 2 sections. Now remember, what was the true value? The true value was 0.1706. My approximate value was 0.1711. I think that is a good approximation. Now I could have solved this question without using any computer actually in the solution. Now, again, let me show you the probability mass function of a Poisson random variable with rate parameter 100. So for a Poisson random variable with rate parameter 100, the probability mass function has this shape, and we are interested in calculating the probability of having more than or equal to 110 students, which is the sum of these probability mass values in the tail, from 110 to infinity. And that is the normal distribution now. So you see the vertical values on the vertical axis are almost the same. This is the normal distribution now. For the normal distribution, our objective is to identify 1 minus the cumulative probability at 109.5. So the probability of this approximate normal random variable to be more than 109.5. That is the probability of the interest, and that is approximated by 0.1711. As you can see, these two values are enoughly close to each other. So this is a good approximation as well.